So just as with simple interest, sometimes we want to determine the other variables in the formula, not just the accumulated amount in the case of compound interest. So how, for instance, would we go about trying to find the principal if we knew all the other parts of the formula? So if we're looking for the principal, think about what the formula is saying. The accumulated amount is equal to the principal times some quantity. That quantity is 1 plus r raised to the power of t. So we just need to divide both sides of that equation by 1 plus r to the power of t, and we're going to get the principal is equal to the accumulated amount divided by 1 plus r to the power of t. So let's go through an example. Let's say we want to end up, or aiming to end up, with an accumulated amount of $10,000. Let's say the time is 8 years, and the interest rate is 4%. So in order to figure out the principal that's required to invest in an account at 4% for 8 years to end up with $10,000, we can just follow the formula on the left where I solved for P. So we have 10,000 in the numerator divided by 1 plus 0.04 to the power of 8. Now, it's very important that you try this a couple of times on whatever calculator you're going to use, because it's very easy to make some mistakes. Some calculators will require you to enter brackets in certain ways, so you got to get comfortable with the calculator that you're using. If you go ahead and calculate 1 plus 0.04, which would be 1.04 raised to the power of 8 first, you're going to have to store that value because you're going to be dividing 10,000 by that value. So however you end up doing it, you should get a value rounded to the nearest penny of $7,306.90. So you should also have a pretty rough idea of what kind of number you're looking for. Obviously, you are expecting a number that is smaller than 10,000 because you're investing 10,000 and then 8 years, sorry, you're investing a certain amount and then 8 years later you're going to get 10,000. So 7,300 is around the sort of right ballpark. It can't be too small, right? We're not doing anything magical with this money. It's only 4% interest per year, and we're only doing this for 8 years. All right, so if you got a result that was too small, like $200, you'd know something was a bit funny there too. So what if we're looking for the rate as opposed to the principal? Well, that's a little bit trickier. So let's go through how you would isolate the term R in the formula. So just as before, the easiest thing to do would be to divide by something on both sides. Now, if we want to get the R on its own, let's just start with the formula. A equals P times 1 plus R to the power of T. If I divide both sides by P, that will allow me to get rid of the P from the right-hand side. And now I have A over P, the accumulated amount over the principal, is equal to 1 plus R to the power of T. Now, you've probably never seen this little step before, but if you know the rules of exponents, it should make sense. How do we get rid of that T and just expose the 1 plus R in the brackets? Well, the way to do that is to raise both sides of this expression to something that will get rid of that T. Now, if you remember your rules of exponents, when you have an exponent and you raise it to another exponent, you multiply those two exponents. So we'd like to get an exponent of just 1 outside the brackets, and the way to do that is to raise this to the power of 1 over T. So if I raise the right-hand side to the power of 1 over T, I need to raise the left-hand side also to the power of 1 over T. And so now I have A over P raised to the power of 1 over T. And these just cancel each other out because T times 1 over T is just 1. And so what I end up with is just 1 plus r. And now it's a very easy step to get r on its own. So now to get r on its own, I just subtract both sides. I subtract 1 from both sides, and I have r equal to a over p to the power of 1 over t minus 1. Okay, so let's try an example here to see if we can come up with something that works. Let's say, using the numbers from the previous example, that we want to end up with an accumulated amount of $10,000. And again, it's going to be over the course of 8 years. But let's say we don't have $7,306.90. Let's, if we're saving up for something that's going to cost $10,000, what if we only have $5,000? So in other words, we've got to double our money. We've got to go from $5,000 to $10,000 in 8 years. Clearly, we're going to need an interest rate that's more than 4%. But what's a good kind of ballpark estimate? Well, this is a bit trickier, and there's a lovely rule that helps us out a lot here to come up with ballpark estimates. And I can't stress how important it is to come up with some sort of estimate before you reach for the calculator, because once you start plugging in numbers to the calculator, whatever the calculator spits out seems like it's got to be true. And I've seen lots of answers that are just patently impossible written down as if they're the gospel truth. So the rule that's going to help us is something called the rule of 72. Now, it's not perfect. It just allows us to come up with estimates. But for sort of normal interest rates in the kind of range that you would see, anywhere from like 1% up to 15%, it's pretty good. And the way the rule of 72 works is it allows you to calculate an interest rate if you know a time, or calculate a time if you know an interest rate. And what it does is it allows you to figure out the time it takes, or the interest rate necessary, to double money. So in this case, we're going from 5,000 to 10,000. We're doubling. And what you do is you take 72 and you divide it by, in this case, 8, the number of years. So 72 over 8 gives us 9, which means that it should be about 9%. It's not going to be exactly, but it's going to be about 9% that we're going to need, which kind of makes sense, right? We're doing a lot more than what we did in the previous example, which is 4%. If we were given an interest rate, let's say we were given an interest rate of 6%, for instance, we would take 72, divide it by 6, and we'd get 12. That would mean you'd need around 12 years in order to double your money. Okay, so let's see if we get an answer that's anywhere close to 9%. So the formula says we're going to take the rate is going to be equal to 10,000 divided by 5,000, which in this case is easy enough to do in our heads. And we're going to raise that to the power of 1 over t. So t is 8, so that's going to be 1 over 8, and then we're going to subtract 1. So, you can certainly do the part in the brackets there in your head. That's just 2, but you won't always be able to do that. 2 to the power of 1/8 minus 1. Now, 2 to the power of 1/8, there's a couple of ways on most calculators that you can do this. Raising something to the power of 1/8 is really the same as taking the 8th root of it. So you might find a button on your calculator that has something like that, or it might even have some variation of that. And so you can certainly use that button, but if you're not really sure about that button, there's always an exponent button. And so you can just raise it to the power of 1/8. But if you're going to use an exponent of 1/8, make sure you put that in brackets. So for instance, some calculators will have something like the following. You'll hit a button that looks like a little caret or up symbol or a circumflex, and then make sure you open the brackets and do 1 divided by 8. Otherwise, you might just end up raising 2 to the power of 1 and then dividing the result by 8. That's not at all what you want to do. So if you've done this correctly, raised 2 to the power of 1/8 and then subtracted 1, you're going to get 0.090507733, etc. It's going to go on for a long time depending on how many decimal places your calculator shows. And there's, unlike money, where it sort of makes sense to round to 2 decimal places, and that represents the nearest penny, there's no hard and fast rules about how many decimal places you should round interest rates to. So if you turn this into a percent, it'd be 9.0 0.0507733%. It's reasonable to round that to 2 decimal places, but I definitely wouldn't round the initial decimal to 2 decimal places. So in other words, if you were looking at the decimal, you'd be rounding it to 4 decimal places. If you're writing it in percentage form, you could round it to 2 decimal places, and you'd get 9.05%. We had an estimate of 9%, and we got 9.05%, which is pretty good. But that was actually kind of a best case scenario for this rule of 72. Okay, so what's the only thing remaining in our formula that we haven't figured out how to solve for? It's t, the time. So if we're trying to find the time, this is tricky, because let's take a look at our formula. We have a equal to p times 1 plus r to the t. Now, how do we get the t on its own? Unfortunately, the way to do this is with a function called logarithms. If you look at your calculator, you may see a button log or another button ln. Either one of those will help you, but we don't learn logarithms in Math 9. You're not going to learn those for a couple of years. So in the meantime, before you have learned about logarithms, the only way to do it is by estimation. So you can start out with something like the rule of 72, get an estimate, try plugging it in to the formula, see if it gives you what you want, and adjust accordingly, either increase it or decrease it. But without logarithms, there's no way to directly calculate t, so we'll just leave it at that.